Hello there, and welcome to another journey into the mysteries that keep us awake at night, or in this case, perhaps gently guide us toward sleep. Tonight, we're not exploring distant galaxies or pondering the nature of black holes. Instead, we're looking right beneath our feet, into the very ground we walk on, and asking a question that might seem simple, but carries profound implications. What if everything we think we know about being first is wrong? Picture this for a moment. You wake up tomorrow morning, brew your coffee, check your phone, go about your day as usual. But what if I told you that millions of years ago, another being might have done something remarkably similar? Not a human, not even close to human, but something else entirely. Something intelligent, curious, perhaps even technological in ways we might not recognize. Something that lived, thrived, built, dreamed, and then vanished so completely that we're only now beginning to ask whether they were ever here at all. This isn't science fiction, though it might sound like it. This is a genuine scientific inquiry that has been quietly percolating through research institutions and academic conferences for years. It's called the Silurian Hypothesis, named somewhat playfully after a fictional species from British television, but grounded in very real questions about geology, paleontology, and the nature of evidence itself. The question we're exploring tonight is both humbling and thrilling. Are we truly the first intelligent civilization to emerge on Earth? Or are we simply the latest in a series that stretches back millions, perhaps tens of millions of years, and if others came before us, would we even know? Would their traces survive the relentless recycling of our planet's surface? Before we dive deeper into this mystery, let me paint you a picture of just how vast the canvas we're working with really is. When we talk about ancient history in everyday conversation, we usually mean a few thousand years. The pyramids of Egypt, the rise and fall of the Roman Empire, the construction of Stonehenge. Even when we stretch back to the very dawn of human civilization, we're talking about maybe 12,000 years since agriculture began to take hold. But 12,000 years is nothing, absolutely nothing, in geological terms. It's a whisper in a symphony that has been playing for over 4.5 billion years. To put this in perspective, if the entire history of Earth were compressed into a single year, human civilization would occupy roughly the last few seconds before midnight on December 31st. Everything we consider ancient history, all of recorded human experience, would fit into the final tick of the clock. For the vast majority of Earth's existence, there were no humans at all. For most of it, there weren't even mammals. Life spent billions of years primarily in the oceans, evolving in forms we can barely imagine, experimenting with countless strategies for survival and reproduction. And during all that time, the planet was writing its own story, layer by layer, in sediment and stone. But here's the thing about our planet that makes this question so intriguing and so difficult to answer. Earth doesn't keep a perfect diary. It's not a passive recorder of events. It's an active, dynamic system that constantly reworks its own surface. Mountains rise and crumble, continents drift apart and collide. Ocean floors spread and get recycled back into the mantle. The face of our world changes completely every few 100 million years. This means that survival, the persistence of any trace or artifact over geological time, is actually an extraordinary exception rather than the rule. Most things that exist on Earth's surface get buried, crushed, melted, eroded, or otherwise destroyed given enough time. The evidence doesn't just fade, it gets actively consumed by the planet's own processes. Consider the fossil record, which is one of our best windows into ancient life. Despite popular images of perfectly preserved dinosaur skeletons, fossils are actually incredibly rare. The conditions required for fossilization are very specific. An organism needs to die in just the right place, get buried quickly in just the right kind of sediment, avoid being disturbed for millions of years, and then be lucky enough to be exposed and discovered by someone who recognizes what they're looking at. Most creatures that have ever lived left no trace whatsoever. They died, decomposed, and returned to the earth without leaving so much as a single bone behind. If this is true for the remains of living organisms, imagine how much more true it must be for the artifacts of intelligence. Tools, buildings, roads, entire cities. All of these are far more fragile than bones and shells. So, when we ask whether another civilization might have existed in the deep past, we're not just asking whether it happened. We're asking whether we could possibly know if it happened. And that's where this mystery becomes truly fascinating, because it forces us to think like detectives working a case where most of the evidence has been deliberately destroyed. In 2018, two scientists named Gavin Schmidt and Adam Frank published a paper that gave this question a formal framework. They weren't claiming that ancient civilizations definitely existed. Instead, they were asking a methodological question. If an industrial civilization like ours had developed 50 or 100 million years ago and then disappeared, what kinds of traces might survive? And would we be able to recognize those traces for what they were? Their approach was clever. Rather than looking for the kinds of obvious artifacts we might expect, pyramids or machines or written records, they focused on something more subtle, but potentially more durable. Chemical signatures, changes in the composition of rocks, sediments, and ice that might indicate large-scale technological activity. Think about what our own civilization is doing to the planet right now. We're changing the composition of the atmosphere by burning fossil fuels. We're creating entirely new materials like plastics that don't exist in nature. We're mining and concentrating rare elements, spreading synthetic chemicals across the globe, and even creating artificial radioactive isotopes through nuclear testing. All of these activities leave chemical fingerprints that get recorded in the layers of sediment being deposited right now. Future geologists, if they exist, will likely be able to see a sharp spike in carbon dioxide levels, traces of synthetic polymers, unusual concentrations of certain metals, and radioactive signatures that mark our brief but intense period of industrial activity. The question Schmidt and Frank posed was this: if similar signatures existed in much older rock layers, would we recognize them as evidence of intelligence? Or would we assume they had natural causes and move on? This is where the detective work gets really interesting, because it turns out that nature itself can produce some surprisingly similar signals. Volcanic eruptions can release massive amounts of carbon dioxide. Asteroid impacts can scatter rare elements across the globe. Natural processes can create complex chemical signatures that might, at first glance, look artificial. So the challenge isn't just finding unusual patterns in ancient rocks. It's developing ways to distinguish between natural anomalies and potential technological signatures. And that requires us to think very carefully about what kinds of evidence would be truly convincing. But before we can even begin that analysis, we need to grapple with an even more fundamental question. What exactly are we looking for? When we say civilization, what do we mean? And would we recognize intelligence if it had evolved along completely different lines than our own? Our typical definition of civilization tends to be quite narrow and, frankly, quite biased toward our own experience. We think of cities, writing systems, metallurgy, monumental architecture. We imagine intelligence that looks more or less like us, using tools and technologies that make sense to us. But intelligence doesn't have to follow our particular path. Consider the remarkable engineering of a termite mound, with its sophisticated ventilation systems and temperature control, or the complex social organization of certain ant species, with their agriculture, architecture, and division of labor. We don't call these civilizations because they don't build with stone or metal, they don't write books, and they don't launch satellites. But what if intelligence had evolved in the ocean? What if it had developed forms of technology based on biological processes rather than mineral extraction? What if it had found ways to manipulate its environment that left traces we wouldn't recognize as artificial? The more we think about it, the more we realize that our assumptions about what intelligence looks like might be severely limiting our ability to recognize it in unexpected forms. This brings us to one of the most profound aspects of this question. It's not just about whether other civilizations existed, it's about the nature of intelligence itself, and whether it's as rare and special as we like to think, or whether it's something that emerges naturally given enough time and the right conditions. If intelligence is rare, if consciousness and technology are cosmic accidents that happened only once on Earth, then we truly are alone and special. But if intelligence is more common, if it's an emergent property that arises naturally in complex systems, then we might be just the latest in a long series of experiments in awareness. The implications of either answer are staggering. If we're alone, it emphasizes just how precious and fragile our civilization really is. If we're not alone, it suggests that intelligence might be woven into the very fabric of how complex systems evolve, and that consciousness might be far more common in the universe than we ever dared to imagine. But here's what makes this question so beautifully mysterious. We might never know for certain. The evidence, if it exists, is subtle, ambiguous, and scattered across billions of years of geological time. We're like archaeologists trying to reconstruct an entire civilization from a few pottery shards, except the pottery shards might be chemical anomalies in rock layers. And the civilization might have been so different from ours that we wouldn't recognize its artifacts even if we found them. And yet, the search itself is valuable, not because it will necessarily give us definitive answers, but because it forces us to think more carefully about evidence, about the nature of intelligence, and about our place in the vast story of our planet. As we continue this exploration, we'll delve deeper into the specific kinds of traces that might survive geological time. We'll examine the forces that erase evidence and the rare conditions that preserve it. We'll look at some of the genuine anomalies that scientists have found in ancient rocks and ask whether any of them might represent something more than natural processes. We'll also explore what our own civilization's signature might look like to future investigators millions of years from now. What would survive of us? What would vanish? And what would future scientists make of the strange chemical spikes and artificial materials we're leaving behind? This is a journey that requires patience, humility, and a willingness to sit with uncertainty. We're not going to find definitive proof of ancient civilizations tonight, but we might find something even more valuable, a sense of wonder about the deep mysteries that surround us, and a deeper appreciation for just how much we still don't know about our own planet. So, settle in, let your thoughts slow down to the pace of geological time, and prepare to explore one of the most intriguing questions science has ever asked. The night is vast, the mystery is deep, and we're just getting started. The first thing we need to understand about searching for traces of ancient intelligence is just how good Earth is at cleaning house. Our planet operates like the ultimate recycling system, constantly breaking down, melting, grinding up, and rebuilding everything on its surface. It's not malicious, just mechanical, but the result is that permanence, as we understand it, is largely an illusion. Let me walk you through what happens to things over deep time, because understanding this process is crucial to grasping why this mystery is so difficult to solve. When we look around us today, we see landscapes that feel eternal, mountains that seem to have always been there, rivers that appear to follow the same paths they always have, bedrock that feels solid and unchanging. But geologists see something entirely different. They see movement in what appears static. They see mountains as temporary accumulations of stone that rise and fall like slow waves. They see rivers as wandering entities that carve new channels and abandon old ones. They see the very ground beneath our feet as something that flows, shifts, and transforms over timescales that dwarf human experience. This transformation happens through several key processes, each one capable of erasing evidence that took millions of years to create. First, there's weathering. Rain, wind, temperature changes, and chemical reactions slowly break down everything exposed to the surface. Even the hardest granite eventually crumbles grain by grain. Steel rusts, concrete cracks, and organic materials decompose. Then there's erosion, which carries away the products of weathering. Rivers transport sediment to the sea. Glaciers scrape entire landscapes clean. Wind redistributes dust across continents. Over time, entire mountain ranges can be worn down to nothing and spread across ocean floors. But perhaps most dramatically, there's the process of plate tectonics. The Earth's outer shell isn't one solid piece. It's broken into massive plates that float on a sea of molten rock deep below. These plates are constantly moving, colliding with each other, pulling apart, and sliding past one another. When they collide, they create mountains and earthquakes. When they pull apart, they create new ocean floor. Most importantly for our mystery, there's a process called subduction, where old ocean floor gets dragged down beneath continents and melted back into the Earth's interior. This means that the oldest parts of the ocean floor, the places where evidence might have accumulated over hundreds of millions of years, eventually get recycled completely. They don't just get buried. They get dissolved back into the planet's molten interior. The average age of the ocean floor is only about 200 million years. That might sound ancient, but remember, Earth is over 4.5 billion years old. This means that most of the sea floor has been completely replaced more than 20 times over during our planet's history. If an ancient civilization had built anything near coastlines, or worse, if it had been primarily oceanic, the evidence might literally have been consumed by the planet itself. Even on the continents where the bedrock is more stable, the surface is constantly being reworked. Sediment accumulates in layers, gets compressed into rock, then gets folded, faulted, and exposed again. Mountains rise from former seafloors. What was once deep underground becomes exposed on mountain peaks. The geological record isn't a neat stack of layers like pages in a book. It's more like a book that's been torn apart, shuffled, had pages removed, and then been bound back together multiple times. This is why the fossil record, our best evidence for ancient life, is so incredibly patchy. It's not that ancient life was rare, it's that the conditions required for preservation are extremely specific and uncommon. Most organisms that die are consumed by scavengers, decomposed by bacteria, or destroyed by chemical processes long before they have any chance of being preserved. To become a fossil, an organism needs to die in just the right place and be buried quickly in just the right kind of sediment. It needs to avoid being disturbed by geological processes for millions of years. Then it needs to be exposed by erosion at just the right time and discovered by someone who recognizes what they're looking at. The odds are astronomical against any individual organism becoming a fossil. Now, imagine trying to preserve not just bones, but artifacts. Tools, buildings, roads, technological devices. These things are generally much more fragile than biological remains. Metals corrode, plastics break down in sunlight, wood rots, fabric decays, even stone structures eventually crumble unless they're in very stable environments. Most of our own artifacts probably won't survive more than a few thousand years unless they're buried in very specific conditions. Dry deserts, frozen tundra, or oxygen-free environments might preserve some materials for longer periods. But over millions of years, the vast majority of everything we've ever built will be gone. This creates what we might call the preservation paradox. The longer ago something happened, the less likely we are to find direct evidence of it. Not because it didn't happen, but because time itself is destructive. The very processes that make Earth a dynamic, living planet also make it an efficient eraser of history. But here's where the detective work gets interesting. While Earth is excellent at destroying physical objects, it's sometimes better at preserving certain kinds of information. Chemical signatures, isotope ratios, elemental concentrations. These can get locked into sediments and preserved for much longer periods than any artifact. When a volcano erupts, it doesn't just create ash and lava. It also releases distinctive chemical signatures that get incorporated into the rocks and sediments of that time period. Millions of years later, geologists can identify these volcanic events by looking at the chemistry of ancient rock layers. Similarly, asteroid impacts leave behind characteristic patterns of rare elements that were scattered globally when the impact occurred. Yeah. The question that Schmidt and Frank were asking is whether technological activity might leave similar chemical fingerprints. When we burn fossil fuels, we're not just releasing carbon dioxide. We're changing the isotopic composition of carbon in the atmosphere in a very specific way. When we manufacture plastics, we're creating molecular structures that don't exist anywhere in nature. When we mine and concentrate rare earth elements for electronics, we're creating unusual distributions of these materials. All of these activities are being recorded right now in the sediments being deposited in lakes, rivers, and oceans around the world. Future scientists will likely be able to see a sharp chemical signature marking our industrial age, even if every city and every machine has long since crumbled to dust. So the real question becomes, if we looked carefully at much older sediments, might we find similar signatures, spikes in atmospheric carbon that happened too quickly to be explained by natural processes? Unusual concentrations of rare elements that don't match known geological patterns? Synthetic molecules that shouldn't exist in nature? This is where the investigation becomes both more hopeful and more challenging. More hopeful because chemical evidence might survive when physical artifacts wouldn't. More challenging because interpreting these chemical signals requires us to distinguish between natural processes and potential technological ones. And nature, it turns out, is capable of producing some surprisingly complex and unusual chemistry all on its own. Massive volcanic eruptions can release enormous amounts of carbon dioxide in relatively short periods. Certain types of microbial activity can create unusual isotope ratios. Hydrothermal vents on the ocean floor can concentrate rare elements in unexpected ways. Even asteroid impacts can create chemical signatures that might, at first glance, look artificial. So finding an unusual chemical pattern in ancient rocks isn't enough. We need to understand whether that pattern could have been produced by known natural processes or whether it requires something else, something that might have been intelligent. This brings us to one of the most fascinating aspects of this investigation. We're not just looking for evidence of ancient technology. We're also learning about the limits of our own scientific methods. How do we distinguish between natural and artificial processes when we're looking at events that happened millions of years ago? How confident can we be in our interpretations when the context has been largely destroyed by geological processes? These are questions that push at the very boundaries of what science can and cannot tell us about the past. They require us to be both rigorously skeptical and genuinely open to possibilities we might not have considered before. As we continue this exploration, we'll look more closely at what kinds of chemical signatures might actually survive over geological time. We'll examine some of the genuine anomalies that scientists have found in ancient rocks, and ask whether any of them might represent more than just unusual natural processes. We'll also need to grapple with the question of what we're actually looking for. If an ancient civilization had evolved along completely different lines than our own, would its technological signature look anything like ours? Or might it be so alien to our experience that we wouldn't recognize it even if we found it? The mystery deepens the more carefully we examine it. But that's exactly what makes it so compelling. We're not just asking whether we're alone in time on our own planet. We're asking fundamental questions about the nature of intelligence, the reliability of evidence, and the humbling vastness of what we still don't know about our own world. The night is patient, and so must we be. There are no easy answers waiting for us, but there are deeper questions, richer mysteries, and perhaps, if we're very lucky, glimpses of truths that might change how we see ourselves and our place in the long, strange story of Earth. When we think about what might survive from an ancient civilization, we have to abandon almost everything we associate with permanence. The grand monuments, the gleaming cities, the intricate machines, all of these would likely crumble into dust long before we arrive to look for them. But there's something else, something more subtle and potentially more enduring that we need to consider. Imagine you're walking through a forest and you come across a clearing where the trees grow in perfectly straight lines. There are no buildings, no obvious signs of construction, but the pattern is too regular to be natural. Something, at some point, imposed order on this landscape. The original structures are gone, but their influence lingers in ways that speak to anyone who knows how to read the signs. This is the kind of evidence we might expect from a truly ancient civilization. Not artifacts, but influences. Not buildings, but patterns. Not machines, but chemistry. The question becomes whether we're sophisticated enough as investigators to recognize these subtle signatures when we encounter them. Let's start with the most basic question. What actually lasts? If we strip away our assumptions about monuments and museums, what kinds of traces might persist across the vast spans of geological time? The answer, surprisingly, often comes down to mistakes and accidents. The most durable signatures of intelligence might not be the things a civilization intended to preserve, but the unintended consequences of their activities, the waste products, the chemical byproducts, the alterations to natural systems that happened as side effects of simply existing at a technological level. Consider plastic, one of our most ubiquitous modern materials. We didn't create plastic to leave a geological signature. We created it to make containers, toys, packaging, countless everyday objects. But plastic has a peculiar property. Certain types are remarkably resistant to decomposition. They break down into smaller and smaller fragments, but the molecular structure remains essentially intact for extraordinarily long periods. Right now, microscopic plastic particles are being incorporated into sediments all over the world. They're settling into lake beds, ocean floors, even polar ice. Future geologists might find thin layers of these synthetic polymers distributed globally across the geological record, marking our industrial age as clearly as volcanic ash marks ancient eruptions. But here's the crucial question. If we found similar synthetic compounds in much older rock layers, would we recognize them as evidence of intelligence? Or would we assume they had some natural origin we didn't yet understand? This question goes to the heart of how science actually works. We have a strong bias toward natural explanations, and for good reason. The history of science is littered with phenomena that seemed mysterious or supernatural until we understood the natural processes behind them. So, when we encounter something unusual in the geological record, our first instinct is always to look for a natural cause. Most of the time, this approach works beautifully, but it also means that we might overlook genuinely artificial signatures if they don't fit our expectations of what intelligence should look like. There's another category of potentially durable evidence that's even more subtle: isotope ratios. These are the relative proportions of different versions of the same chemical element, and they can serve as fingerprints for different types of processes. When we burn fossil fuels, we're not just releasing carbon dioxide into the atmosphere. We're releasing carbon dioxide with a very specific isotopic signature. Fossil carbon has been isolated from the atmosphere for millions of years, so it has a different ratio of carbon-12 to carbon-13 than carbon that's been cycling through living systems. This signature gets preserved in ice cores, sediments, and even the shells of marine organisms. If an ancient civilization had burned carbon-based fuels on a massive scale, it might have left behind a similar isotopic signature. A sharp change in carbon ratios that happened too quickly to be explained by gradual natural processes. The challenge, of course, is that there are natural events that can also produce rapid changes in atmospheric chemistry. Massive volcanic eruptions, for instance, or the sudden release of methane from ocean sediments. Distinguishing between natural and potentially artificial signatures requires incredibly careful analysis and often additional lines of evidence. A single anomalous measurement means little. But multiple independent signatures that all point in the same direction, that tell a consistent story of rapid, large-scale change, these might be worth investigating more carefully. Then there are the rare earth elements, the exotic materials that our modern technology depends on. Smartphones, computers, advanced batteries, all of these require elements like neodymium, dysprosium, and terbium. These elements are naturally rare, but our industrial processes concentrate them in unusual ways. Mining and refining these materials creates waste products with very distinctive chemical signatures. If we found ancient sediments with unusually high concentrations of these elements, especially in patterns that suggested processing rather than natural weathering, it might indicate technological activity. But again, interpretation is everything. Many of these same elements are concentrated by natural processes. Hydrothermal vents, certain types of volcanic activity, even some biological processes can create unusual elemental distributions. The key is learning to distinguish between patterns that could occur naturally and patterns that require deliberate intervention. This brings us to one of the most intriguing possibilities. What if an ancient civilization had developed along completely different technological lines than our own? What if they had never discovered metallurgy, never learned to extract and work metals from ore? Would we even recognize their technology as technology? For most of human history, we lived without metals. Our ancestors created sophisticated tools from stone, bone, and wood. They built complex societies, developed agriculture, created art and music and stories. They were intelligent, creative, and technologically capable within the constraints of their materials. Now, imagine scaling that up. What if a species had evolved sophisticated biotechnology instead of mechanical technology? What if they had learned to domesticate and modify organisms for their purposes, creating living tools instead of manufactured ones? What if their great works were forests and ecosystems rather than cities and machines? Such a civilization might leave traces that we would interpret as purely biological. Modified plant species growing in unnatural distributions. Soil chemistry altered by deliberate cultivation. Erosion patterns that suggest landscape management on a massive scale. But without the context of metal tools and stone buildings, would we recognize these patterns as evidence of intelligence? This possibility forces us to confront our own biases about what technology should look like. We assume that intelligence naturally leads to metallurgy, that sophistication requires the manipulation of inorganic materials. But this assumption is based on a sample size of exactly one, our own species' particular path through the space of possible technologies. Intelligence might be much stranger and more diverse than we imagine. It might take forms that don't leave the kinds of signatures we know how to look for. It might work with natural systems rather than against them, shaping environments in ways that appear organic even when they're deliberately designed. Consider the terra preta soils of the Amazon basin. These are areas of extraordinarily fertile black earth that were created by indigenous peoples over centuries of careful land management. They contain charcoal, bone fragments, pottery shards, and complex organic chemistry that continues to enrich the soil even today. To a casual observer, they might look like natural formations, but they represent sophisticated agricultural technology that sustained large populations for hundreds of years. If similar soil engineering had been practiced on a larger scale millions of years ago, and if the pottery and bone fragments had long since decomposed, would we recognize the remaining chemical signatures as evidence of deliberate cultivation? Or would we classify them as interesting but unexplained variations in soil chemistry? The more we think about this problem, the more we realize that evidence of ancient intelligence might be hiding in plain sight, misclassified as natural phenomena, because we don't have the conceptual framework to recognize it as artificial. This doesn't mean we should abandon scientific rigor or start seeing intelligence everywhere we look. It means we need to be more creative and more humble about the possibilities. We need to develop better methods for distinguishing between natural and artificial patterns, and we need to remain open to the possibility that intelligence might not always look the way we expect it to. There's also the question of scale and duration. How long would a civilization need to exist to leave detectable traces? How large would it need to be? These questions don't have simple answers because they depend entirely on what kinds of activities the civilization engaged in and what kinds of environments they lived in. Our own industrial civilization has been altering the planet's chemistry for only about 2 centuries, but the changes are already dramatic and globally distributed. we've altered the composition of the atmosphere, the chemistry of the oceans, and the distribution of elements across the Earth's surface. Even if our civilization ended tomorrow, some of these signatures would persist for thousands, possibly millions of years. But a civilization that developed along different lines might leave much subtler traces, or traces that are concentrated in specific regions rather than distributed globally. They might have existed for much longer periods while leaving lighter footprints, or they might have been more transient but left more intense local signatures. The detective work becomes even more complex when we consider that any ancient civilization would have existed in a very different world than our own. The continents were in different positions. The climate was different. The composition of the atmosphere was different. Even the length of the day was different, because the Earth was spinning faster. These differences matter because they affect both what kinds of traces might be preserved and where we should look for them. Coastlines that existed millions of years ago are now deep underwater or have been pushed up into mountain ranges. Sedimentary basins that might have preserved evidence have been folded, faulted, and eroded. The very geography of preservation has been scrambled by geological time. This is why the search for ancient intelligence is simultaneously one of the most intriguing and most challenging questions in science. We're looking for subtle signals in a record that has been systematically disrupted. We're trying to recognize patterns that might not match our expectations. We're working at the absolute limits of what evidence can tell us about the past. But perhaps that's exactly why this question is so valuable. It forces us to think more carefully about the nature of evidence itself. It challenges our assumptions about intelligence and technology. It reminds us that the universe might be far stranger and more wonderful than our current theories suggest. As we continue this exploration, we'll delve deeper into the specific kinds of anomalies that scientists have actually found in ancient rocks. We'll examine whether any of these might represent something more than natural processes. We'll also consider what our own civilization's signature will look like to future investigators, and what that might teach us about the possibilities we're searching for. The night is deep, the mystery is vast, and we're only beginning to scratch the surface of what might be hidden in the long, silent history of our planet. But sometimes, in science, as in sleep, the most profound discoveries come not from forcing answers, but from learning to ask better questions. The silence in ancient sediments speaks in whispers, and learning to hear those whispers requires us to become fluent in the language of deep time itself. It's a language written not in words, but in chemistry, not in sentences, but in the subtle variations of elements that accumulated grain by grain over millions of years. When geologists drill core samples from lake beds or ocean floors, they're essentially extracting libraries from the earth. Each layer represents a moment in time, a thin slice of history compressed into sediment. The thickness of the layer tells us about the rate of deposition. The color might indicate the amount of organic matter or the presence of certain minerals. The chemistry revealed the composition of the atmosphere and oceans when that layer was formed. But reading this library requires extraordinary patience and sophisticated tools. A single core sample might represent millions of years of history compressed into just a few meters of rock and sediment. The resolution is necessarily coarse. Events that lasted centuries might be compressed into layers only millimeters thick. Entire civilizations could rise and fall in what appears as a barely detectable blip in the chemical record. This is where the search for ancient intelligence becomes almost philosophical. We're not looking for smoking guns or obvious artifacts. We're looking for patterns that shouldn't be there, anomalies that break the rhythm of natural processes, a sudden spike in carbon levels that happen too quickly for gradual climate change, an unusual concentration of rare metals with no obvious geological source, isotope ratios that don't match any known natural process. The challenge is that nature itself is incredibly creative. Volcanic eruptions can release massive amounts of carbon dioxide in geologically brief periods. Meteorite impacts can scatter exotic elements across the globe. Even microbial activity can create unusual chemical signatures under the right conditions. The boundary between natural and artificial becomes blurry when you're working with evidence that's millions of years old. Consider what scientists call the Paleocene-Eocene thermal maximum, an event that occurred about 56 million years ago. During this period, global temperatures rose dramatically, ocean chemistry changed, and there was a massive disruption in the carbon cycle. The chemical signature of this event is clearly visible in sediment cores from around the world. It shows all the hallmarks of what we might expect from large-scale industrial activity: rapid warming, ocean acidification, and strange carbon isotope ratios. Yet, as far as we know, no civilization was involved. The event appears to have been caused by natural processes, possibly the sudden release of methane from ocean sediments or massive volcanic activity. It serves as a sobering reminder that Earth's natural systems can produce signatures that might, in other contexts, look suspiciously artificial. But it also demonstrates something important. Even after 56 million years, the chemical fingerprint of this event is still clearly readable in the geological record. If a technological civilization had existed and had altered global chemistry on a similar scale, we might still be able to detect it today. The key word there is might, because preservation, even of chemical signatures, is never guaranteed. Sediment layers can be disturbed by earthquaking or erosion. Chemical compositions can be altered by groundwater or biological activity. The very processes that create rocks can scramble or destroy the signals we're looking for. This uncertainty is both frustrating and oddly liberating. It means we can never definitively prove that ancient civilizations didn't exist. The absence of evidence truly isn't evidence of absence when working at these time scales. But it also means that any positive evidence needs to be extraordinarily compelling to overcome our natural skepticism. There's another layer of complexity that makes this investigation even more challenging. We're not just looking for evidence of technology as we understand it. We're potentially looking for evidence of intelligence that might have operated by completely different principles. Imagine, for instance, a civilization that never discovered fire. This might sound impossible to us because fire has been so central to human development. But there are environments where fire might be unnecessary or even counterproductive. An aquatic civilization, for example, might develop entirely different approaches to energy and materials processing. Or consider a civilization that developed what we might call biological technology. Instead of mining metals and building machines, they might have learned to breed and modify organisms for their purposes. They might have created living computers, organic materials, with properties that we achieve through industrial processes. Transportation systems based on trained creatures rather than mechanical vehicles. Such a civilization might leave traces that we would interpret as purely biological. Unusual genetic diversity in certain species, organisms with traits that seem too sophisticated to have evolved naturally, ecosystem structures that appear designed rather than emergent. But without the context of familiar technologies, we might never recognize these patterns as evidence of intelligence. This possibility becomes even more intriguing when we consider the time scales involved. Our own technological civilization has existed for only a few centuries, but a biological civilization might persist for much longer periods while leaving much subtler traces. They might achieve sustainability in ways that we're only beginning to understand, working with natural cycles rather than disrupting them. The Amazon rainforest provides a fascinating example of how this might work. Recent research has revealed that much of what we considered pristine wilderness was actually shaped by indigenous peoples over thousands of years. They created complex agroforestry systems, managed fire patterns, and even engineered soils to maintain fertility over centuries. The forest we see today is as much a product of human intelligence as it is of natural processes. But this management was so sophisticated, so well integrated with natural systems, that it took modern science decades to recognize it as artificial. If similar landscape engineering had been practiced on a global scale millions of years ago, would we have any hope of detecting it today? The answer depends partly on scale and partly on our ability to recognize patterns that don't match our preconceptions. A truly ancient civilization might have left signatures so subtle, so well integrated with natural processes, that we've been looking at the evidence for years without recognizing what it represents. There's also the humbling possibility that some of the anomalies we've already found in the geological record might be exactly what we're looking for, but we lack the conceptual framework to interpret them correctly. Science has a long history of discoveries that were initially overlooked because they didn't fit existing theories. Continental drift was proposed in the early 20th century, but wasn't accepted until the 1960s, when new evidence made it impossible to ignore. The impact theory for dinosaur extinction was considered fringe science until the discovery of the iridium layer provided compelling evidence. Even the existence of giant squids was considered mythical until relatively recently. Each of these discoveries required scientists to expand their thinking, to consider possibilities that seemed unlikely or even impossible given the prevailing understanding of how the world works. The search for ancient intelligence might require a similar conceptual leap. But this doesn't mean we should abandon scientific rigor. or start seeing intelligence in every unusual pattern. It means we need to be simultaneously more creative and more careful in our investigations. We need to develop better methods for distinguishing between natural and artificial processes. We need to expand our definition of what intelligence might look like while maintaining strict standards for evidence. The ocean presents a particularly intriguing case study for these challenges. More than 70% of our planet's surface is covered by water, yet we've explored less than 5% of the ocean floor. We know more about the surface of Mars than we do about the deep ocean basins of our own planet. If an ancient civilization had been primarily oceanic, or if they had built cities along coastlines that are now submerged, we might never find direct evidence of their existence. The ocean is a particularly harsh environment for preservation. Salt water corrodes metals rapidly. Biological activity breaks down organic materials. Ocean currents redistribute sediments, burying some areas while scouring others clean. Even more dramatically, the ocean floor itself is temporary. The process of seafloor spreading means that new ocean floor is constantly being created at mid-ocean ridges, while old ocean floor is consumed at subduction zones. The oldest parts of the current ocean floor are only about 200 million years old. Anything older has been recycled back into the Earth's interior. This means that if an ancient civilization had existed more than 200 million years ago and had left traces on the ocean floor, those traces would now be melted rock deep within the Earth's mantle, not buried, not hidden, but literally dissolved back into the planet's molten interior. Yet the ocean also offers unique opportunities for preservation. Deep ocean basins can accumulate sediments continuously for millions of years without major disturbance. These sediments preserve detailed records of ocean chemistry, atmospheric composition, and even biological productivity. If an ancient civilization had altered global chemistry, traces of those changes might still be detectable in deep ocean sediment cores. Some of the most intriguing possibilities involve what we might call technological fossils. These wouldn't be the remains of machines or buildings, but the chemical and isotopic signatures of industrial processes. The synthetic molecules that don't occur in nature, the unusual elemental concentrations that result from mining and refining, the distinctive patterns of pollution that accompany large-scale manufacturing. Our own civilization is creating these technological fossils right now. Plastic particles are accumulating in sediments worldwide. Radioactive isotopes from nuclear testing are being incorporated into the shells of marine organisms. The carbon isotope signature of fossil fuel burning is being recorded in ice cores and tree rings. Future scientists will likely be able to identify our industrial age as a distinct geological event, a sharp transition in the chemistry of Earth's surface systems. The question is whether similar transitions might be hidden in much older parts of the geological record, but finding these signatures requires us to know what to look for, and that's where the investigation becomes circular. We're looking for evidence of technology, but we can only recognize the kinds of technological signatures that we ourselves produce. An ancient civilization that developed along completely different lines might have left traces that we wouldn't even think to investigate. This limitation forces us to be both more systematic and more imaginative in our approach. We need to catalog all the ways that intelligence might alter natural systems, not just the ways that our particular form of intelligence has altered them. We need to look for patterns that suggest deliberate intervention, even if we can't immediately understand what kind of intervention it might have been. The search also requires us to think carefully about time scales and preservation. Different types of evidence survive for different lengths of time under different conditions. Organic molecules might preserve for thousands of years in frozen environments, but decompose rapidly in warm, wet conditions. Metal artifacts might last for centuries in dry climates, but corrode quickly in humid ones. Chemical signatures in sediments might persist for millions of years if the sediments remain undisturbed, but could be altered or destroyed by geological activity. Understanding these preservation biases is crucial because they determine not just what we might find, but where and how to look for it. The best preserved records come from stable, low-energy environments. Deep lake beds, polar ice, cave deposits, arid regions where chemical and biological activity is minimal. But these environments represent only a tiny fraction of Earth's surface. Most of the planet's history is recorded in environments that are much more dynamic, much more prone to disturbance and alteration. The signals we're looking for might exist, but they might be degraded, scattered, or mixed with so much background noise that they're impossible to extract. This brings us back to the fundamental challenge of this investigation. We're looking for subtle signals in a record that has been systematically disrupted. We're trying to recognize patterns that might not match our expectations. We're working at the absolute limits of what evidence can tell us about events that happened millions of years ago. Yet, perhaps that's exactly what makes this question so compelling. It pushes us to develop new methods, to think more creatively about evidence, to consider possibilities that we might otherwise dismiss. It reminds us that the universe is under no obligation to make sense according to our current understanding, and that the most profound discoveries often come from investigating the things that don't quite fit our existing theories. The night grows deeper, and our journey into these ancient mysteries continues. We've explored the challenges of preservation and the subtlety of chemical signatures. We've considered the possibility that intelligence might take forms we wouldn't immediately recognize. But there are still deeper questions waiting for us. Questions about the nature of evidence itself and the limits of what we can know about our planet's distant past. In the sediments and the silence, in the chemistry and the stone, there might be stories waiting to be told, stories of minds that wondered and built and dreamed long before we existed. Or perhaps there are only the patient processes of geology, writing their own slow tales in languages we're still learning to read. Either way, the search itself changes us. It makes us more humble about our place in time, more careful about our assumptions, more willing to sit with uncertainty and wonder. And in a world that often demands quick answers and simple explanations, perhaps that willingness to embrace mystery is exactly what we need. The deeper we dig into this mystery, the more we realize that we're not just investigating the possibility of ancient civilizations. We're investigating the very nature of memory itself. How does a planet remember? What kinds of information can survive the constant churning of geological processes? And perhaps most unsettling of all, what might we be forgetting even as we search? There's something profound about the way Earth stores information, unlike human memory, which can be vivid and immediate. Geological memory is patient and indirect. It doesn't preserve events so much as it preserves consequences. The impact that created the Chicxulub crater didn't leave behind a record of the asteroid itself, but it left behind a thin layer of shocked quartz and iridium scattered across the globe. The event is gone, but its signature endures in the chemistry of the rocks. This indirect preservation creates a peculiar challenge for anyone trying to read the deeper history of intelligence on our planet. We're not looking for libraries or monuments or any of the obvious traces that intelligence might leave behind. We're looking for the unintended consequences, the chemical fingerprints, the subtle alterations to natural systems that might indicate something was here, doing something deliberate long before we arrive to wonder about it. Consider what we know about our own impact on the planet's memory systems. Right now, as you listen to these words, processes are occurring that will be readable millions of years from now. Every time we burn coal or oil, we're altering the isotopic composition of carbon in the atmosphere. Every plastic bottle that ends up in the landfill is creating microscopic particles that will be incorporated into sediments for thousands of years. Every nuclear test conducted during the 20th century scattered artificial isotopes that are still detectable in ice cores and deep ocean sediments. Future geologists, if they exist, will likely see our industrial age as a sharp discontinuity in the planet's chemical record, a sudden spike in atmospheric carbon dioxide, a global distribution of synthetic polymers, radioactive signatures that have no natural explanation. They might not understand what caused these changes, but they'll know that something dramatic happened during our brief moment on the geological stage. The question that haunts this investigation is whether similar signatures might already exist in much older parts of the record. Signatures that we've either overlooked or misinterpreted as natural phenomena. The challenge is that nature itself is remarkably creative in the kinds of chemical patterns it can produce. Take the Great Oxidation Event, which occurred roughly 2.5 billion years ago. During this period, the composition of Earth's atmosphere changed dramatically as photosynthetic organisms began producing oxygen on a massive scale. The chemical signature of this event is clearly visible in the geological record. Iron formations changed color as iron began reacting with the newly abundant oxygen. Sulfur isotope ratios shifted in characteristic ways. The entire chemistry of the planet's surface was transformed. From our perspective, this was clearly a biological event caused by the evolution of cyanobacteria and their ability to photosynthesize. But imagine if we didn't know about photosynthesis, if we encountered this chemical signature without understanding its biological origin, we might wonder whether it represented some kind of technological activity. A massive atmospheric engineering project, perhaps, or industrial processes operating on a planetary scale. This example illustrates both the promise and the peril of searching for ancient technological signatures. The promise is that truly global alterations to Earth's chemistry can indeed be preserved for billions of years. The peril is that biological and geological processes can produce signatures that might, in other contexts, appear technological. The boundary between natural and artificial becomes even more complex when we consider the possibility of what we might call biotechnological civilizations. What if an ancient intelligence had learned to work with living systems rather than against them? What if they had developed technologies based on modifying organisms rather than manufacturing machines? We're already seeing hints of this possibility in our own world. Genetic engineering allows us to create organisms with novel properties. Synthetic biology is beginning to produce living systems that can manufacture chemicals, process information, even serve as construction materials. It's not difficult to imagine a civilization that took this approach much further, creating entire ecosystems designed to serve technological purposes. Such a civilization might leave traces that we would classify as purely biological. Unusual genetic sequences that appear too complex to have evolved naturally. Organisms with capabilities that seem engineered rather than evolved. Ecosystem structures that appear designed for specific functions. But without the context of familiar mechanical technologies, we might never recognize these patterns as evidence of intelligence. The Amazon rainforest offers a tantalizing example of how subtle these traces might be. Recent research has revealed that much of what European explorers considered pristine wilderness was actually a carefully managed landscape. Indigenous peoples had been shaping the forest for thousands of years, creating complex systems of agriculture, forestry, and soil management that sustained large populations while maintaining ecological diversity. The evidence for this management is everywhere once you know how to look for it. Certain tree species are distributed in patterns that suggest deliberate cultivation. Soil chemistry shows signs of intentional enrichment with charcoal and organic matter. Even the genetic diversity of some plants appears to have been shaped by human selection over many generations. But for centuries, scientists interpreted these patterns as natural. The idea that indigenous peoples could have engineered landscapes on such a vast scale didn't fit prevailing assumptions about primitive societies and untouched nature. It took decades of careful research and a fundamental shift in thinking to recognize the sophisticated technology hidden in what appeared to be wilderness. If similar landscape engineering had been practiced on a global scale millions of years ago, and if the more obvious artifacts had long since decomposed, would we have any hope of recognizing what remained? The chemical signatures in ancient soils might tell a story of deliberate cultivation, but we might interpret them as natural variations in geological processes. This possibility forces us to confront our own biases about what intelligence should look like and what kinds of traces it should leave behind. We assume that technological advancement necessarily involves the extraction and manipulation of inorganic materials. We expect intelligence to leave behind durable artifacts made of stone or metal. But these assumptions are based on our own particular evolutionary path. Intelligence might be far more diverse and subtle than we imagine. It might work with natural systems rather than replacing them. It might achieve sophisticated results through biological processes rather than mechanical ones. It might even deliberately minimize its impact on the geological record, either out of environmental consciousness or as a survival strategy. There's also the troubling possibility that we might be looking at evidence of ancient intelligence right now without recognizing it for what it is. The geological record is full of patterns and anomalies that don't have entirely satisfactory natural explanations. Most of these are probably the result of processes we don't yet fully understand, but some might represent something else entirely. Consider the banded iron formations that appear in rocks from the early Earth. These structures show regular patterns of iron-rich and iron-poor layers that suggest cyclical processes operating over millions of years. The conventional explanation involves complex interactions between ocean chemistry, biological activity, and atmospheric composition. But the regularity of these patterns is striking, almost engineered in appearance. Or consider the unusual isotope ratios found in certain meteorites, which suggest that the early solar system contained materials with properties that are difficult to explain through known stellar processes. Most scientists assume these represent natural processes that we don't yet understand. But the assumption itself is worth examining. The challenge is developing criteria for distinguishing between natural processes that we don't understand and potential technological signatures from the deep past. This requires us to be simultaneously more open-minded and more rigorous in our analysis. We need to consider possibilities that might seem unlikely while maintaining strict standards for evidence. Part of the difficulty lies in the nature of scientific training itself. We're taught to look for the simplest explanation that fits the available evidence. This approach has served science well, helping us avoid the trap of seeing design and intention where none exists. But it might also make us systematically blind to genuine signatures of intelligence if those signatures don't match our expectations. The search for ancient intelligence requires a different kind of thinking, one that's comfortable with ambiguity and uncertainty. We're not looking for proof because proof might be impossible given the limitations of the geological record. We're looking for patterns that are suggestive, anomalies that deserve further investigation, possibilities that expand our understanding of what intelligence might look like and how it might manifest. This approach requires extraordinary humility. We have to acknowledge that our current understanding of natural processes is incomplete, that our assumptions about intelligence might be parochial, and that the absence of evidence is not necessarily evidence of absence. We have to be willing to sit with questions that might never have definitive answers. But perhaps that willingness to embrace uncertainty is exactly what this investigation offers us. In a world that often demands quick solutions and simple explanations, the search for ancient intelligence reminds us that some mysteries are worth preserving. Some questions are more valuable than their answers because they keep us humble, curious and open to possibilities we haven't yet imagined. The geological record stretches back over 4 billion years, representing a vast library of information about our planet's history. Most of that library remains unread, not because we lack the tools to examine it, but because we're only beginning to understand the languages in which it's written. Chemical signatures, isotope ratios, mineral distributions, these are dialects in a vast conversation that the earth has been having with itself since long before life appeared on its surface. If intelligence arose multiple times during that vast span of history, its signatures might be scattered throughout that library, waiting for investigators sophisticated enough to recognize them. Or they might have been erased entirely by the relentless processes of geological recycling. Or they might be hiding in plain sight, misclassified as natural phenomena, because we lack the conceptual framework to see them as anything else. The beauty of this uncertainty is that it keeps the question alive. It prevents us from closing the book on possibilities that might transform our understanding of intelligence, consciousness, and our place in the cosmic story. It reminds us that the universe is under no obligation to conform to our current theories, and that the most profound discoveries often come from investigating the things that don't quite fit. As we continue this journey through deep time and deeper mysteries, we'll explore what our own civilization's signature might look like to future investigators. We'll examine the forces that preserve evidence and the forces that destroy it. We'll consider what it means to search for something that might not exist, and what it teaches us about the nature of knowledge itself. The night is patient, and so must we be. In the silence between heartbeats, in the space between thoughts, there might be echoes of minds that wondered and built and dreamed long before we existed. Or there might be only the patient processes of chemistry and time, writing their own slow stories in languages we're still learning to speak. Either way, the search changes us. It makes us more aware of our assumptions, more careful with our conclusions, more willing to live with questions that have no easy answers. And in a cosmos vast beyond imagination, perhaps that willingness to wonder is the most human thing of all. There's something almost dreamlike about the way evidence behaves across geological time. It doesn't disappear all at once, like a candle being blown out. Instead, it fades gradually, selectively, leaving behind fragments that tell incomplete stories. A tool might survive while the hand that made it turns to dust. A chemical signature might persist while the civilization that created it becomes unimaginable. This selective preservation creates what we might call the archaeology of whispers. We're not looking for shouts from the past, clear declarations of intelligence and purpose. We're listening for murmurs, hints, the faintest suggestions that something once was here, thinking and building and changing the world in ways that left traces too subtle for casual observation. Consider how our own whispers are being written into the planet's memory right now. Every smartphone contains dozens of rare earth elements extracted from mines scattered across the globe. When these devices eventually end up in landfills, They create concentrated deposits of materials that don't occur together in nature. Neodymium next to lithium, next to tantalum, all in ratios and combinations that would never arise through geological processes alone. Future archaeologists might find these technological graveyards and wonder what kind of civilization needed so many exotic elements in such precise combinations. They might not understand what smartphones were, but they'd recognize the signature of deliberate extraction and concentration, the fingerprint of intelligence manipulating matter for purposes that natural selection never intended. But here's the unsettling question. If we found similar exotic element concentrations in much older rock formations, would we recognize them as technological signatures? Or would we assume they represented some unknown natural process and file them away as geological curiosities? The answer depends partly on context and partly on our willingness to consider uncomfortable possibilities. Science has a built-in conservatism that serves us well most of the time. When we encounter something unusual, our first instinct is to look for conventional explanations. This approach prevents us from seeing miracles where none exist, from attributing natural phenomena to supernatural causes. But this same conservatism might blind us to genuine anomalies that don't fit our current understanding of how the world works. If an ancient civilization had developed technologies we can't imagine, using principles we haven't discovered, their traces might be scattered throughout the geological record, dismissed as natural oddities, because we lack the theoretical framework to recognize them as artificial. The problem becomes even more complex when we consider the possibility of non-human intelligence. We tend to assume that any technological civilization would develop along roughly similar lines to our own. They would discover fire, develop metallurgy, build cities, create writing systems. But this assumption reflects our own evolutionary path, not any universal law of intelligence. What if intelligence had emerged in the deep ocean, where fire is impossible and metals are scarce? What if it had developed in environments where cooperation was more advantageous than competition, leading to technologies based on collective behavior rather than individual tools? What if it had evolved in creatures with radically different sensory capabilities, leading to technologies we literally cannot perceive? These possibilities stretch our imagination, but they're not scientifically unreasonable. Intelligence is an emergent property of complex systems, and complex systems can organize themselves in countless different ways. The particular form of intelligence we represent, tool-using, language-speaking, technology-building primates, is just one possible solution to the problem of survival and reproduction. If intelligence had evolved along different lines, its traces might be everywhere around us, but written in languages we don't know how to read. The migration patterns of certain species might encode information about ancient climate management. The genetic diversity of plants might reflect selection pressures imposed by long-vanished cultivators. The distribution of minerals might tell stories of mining operations that used biological rather than mechanical processes. This possibility forces us to expand our definition of what we're looking for. We're not just searching for familiar technologies implemented by unfamiliar beings. We're potentially searching for unfamiliar technologies that might not look like technology at all. At least not to eyes trained to recognize the mechanical and electronic systems of our own civilization. The ocean presents particularly intriguing possibilities in this regard. Water covers more than 70% of our planet's surface, yet we've explored less than 5% of the deep ocean. We know more about the surface of Mars than we do about the abyssal plains of our own world. If intelligence had evolved in these vast underwater realms, we might never encounter direct evidence of its existence. But even oceanic civilizations might leave traces detectable on land. Ocean chemistry affects atmospheric composition, which in turn gets recorded in ice cores and sediment layers. Large-scale underwater agriculture might alter nutrient cycles in ways that show up in the fossil record of marine organisms. Even purely aquatic technologies might create chemical signatures that eventually make their way into the geological record we can access. The challenge lies in learning to recognize these indirect signals. We need to think like detectives investigating a crime scene where most of the evidence has been deliberately obscured. We have to look for patterns that don't quite fit, anomalies that suggest intervention, signatures that are too regular or too concentrated to be entirely natural. This detective work requires us to become fluent in multiple scientific languages simultaneously. Geochemistry, to understand how chemical signatures are created and preserved. Paleoclimatology, to distinguish between natural climate variations and potential artificial ones. Evolutionary biology, to recognize when species distributions or genetic patterns might reflect intelligent intervention rather than natural selection. But perhaps most importantly, it requires us to develop what we might call imaginative rigor, the ability to consider possibilities that stretch conventional thinking while maintaining strict standards for evidence, the willingness to take seriously ideas that might seem unlikely while avoiding the trap of seeing intelligence where none exists. This balance is delicate and difficult to maintain. It's easy to swing too far in either direction, either dismissing all anomalies as natural variations or seeing technological signatures in every unusual pattern. The middle ground requires constant vigilance, careful analysis, and the humility to acknowledge when we simply don't know. There's also the question of motivation. Why does this investigation matter? What would it mean if we discovered that intelligence had indeed arisen multiple times on our planet? The implications would ripple through every field of human knowledge, from biology and geology to philosophy and theology. If intelligence is common, if consciousness emerges naturally from sufficiently complex systems, then we might not be as special as we like to think. But we also might not be as alone. The universe might be filled with minds wondering and building and dreaming, each following their own evolutionary path toward complexity and awareness. Alternatively, the discovery might make us feel more unique, not less. If other intelligences had arisen and then vanished, leaving only the faintest traces behind, it would underscore just how fragile consciousness really is, how easily it can emerge from the intricate dance of matter and energy, and how easily it can disappear back into silence. Either possibility would change how we see ourselves and our responsibilities. If intelligence is rare, we bear the burden of preserving and nurturing one of the universe's most precious experiments. If intelligence is common but fragile, we bear the responsibility of learning from the mistakes of our predecessors, of finding ways to persist where they could not. But perhaps the most profound impact would be on our understanding of time itself. We think of history as something that begins with written records, of civilization as something that started just a few thousand years ago. The discovery of much older intelligences would force us to reconceptualize our place in the vast story of our planet. We would no longer be the protagonists of Earth's story, the first characters to appear on stage. We would be part of a much longer narrative, perhaps just the latest chapter in a book that began millions of years before we existed. The humility required to accept such a perspective might be exactly what our species needs as we grapple with our own impact on the planet's future. There's something beautiful about this uncertainty, this vast space of not knowing that opens up when we seriously consider the possibility of ancient intelligence. It prevents us from becoming too comfortable with our assumptions, too confident in our theories about how the world works. It keeps alive a sense of wonder about our own planet, reminding us that even the ground beneath our feet might hold secrets we've never imagined. The investigation also reveals something important about the nature of scientific inquiry itself. We often think of science as a process of finding answers, of reducing uncertainty and replacing mystery with knowledge. But the search for ancient intelligence suggests that science might be equally valuable as a way of asking better questions, of opening up new spaces for wonder and investigation. Some mysteries might be more valuable than their solutions. Some questions might teach us more by remaining open than they would by being definitively answered. The possibility of ancient intelligence is one of these questions. Whether or not we ever find convincing evidence, the search itself changes how we think about intelligence, consciousness, and our place in the cosmic story. It makes us more careful observers of the world around us, more willing to consider possibilities that challenge our assumptions, more humble about the limits of our current knowledge. It reminds us that the universe is vast and strange and full of possibilities we haven't yet learned to imagine. As we continue this journey through deep time and deeper mysteries, we'll explore what happens when civilizations end. Not just how they disappear, but what kinds of traces they leave behind and how those traces get incorporated into the planet's long memory. We'll consider what our own ending might look like and what future investigators might make of the strange chemical spikes and artificial materials we're leaving scattered through the geological record. The night deepens around us, and the questions multiply like stars in a darkening sky. Each answer we find opens up new mysteries, new possibilities, new reasons to keep searching. In the silence between one thought and the next, in the space between heartbeats, there might be echoes of minds that wondered about these same questions millions of years before we existed. Or there might be only the patient processes of chemistry and time, writing their own slow stories in languages we're still learning to speak. Either way, the search continues, carrying us deeper into the mystery of what it means to be conscious in a universe that seems, most of the time, to be dreaming of itself. When we imagine the end of civilizations, we tend to picture dramatic collapses, cities burning, populations fleeing, great libraries crumbling into dust. But the reality of how intelligence disappears from the geological record is often much quieter, much more gradual, and far more complete than our dramatic imagination suggests. Think about it this way. Right now, as we speak, there are processes occurring that will determine what future investigators might find of us millions of years from now. Not the grand monuments we build or the complex technologies we create, but the accidental byproducts of simply existing at an industrial scale, the carbon we're releasing into the atmosphere, the synthetic materials we're scattering across the planet's surface, the isotopic signatures we're creating through nuclear processes. These traces are being written into the Earth's memory systems as we live our daily lives, completely independent of our intentions or desires for how we might be remembered. A plastic water bottle discarded today might become a microscopic fragment embedded in sediments that won't be exposed for millions of years. The exhaust from a single car trip becomes part of an atmospheric signature that's being recorded in ice cores and ocean chemistry. But here's what makes this so fascinating and so unsettling. If our own civilization ended tomorrow, most of what we consider important about ourselves would vanish almost immediately. Our art, our literature, our music, our digital archives, all of the content that we think defines our culture would disappear within decades or centuries. What would persist are the things we barely think about. The waste, the pollution, the chemical alterations to natural systems that we treat as unfortunate side effects rather than defining characteristics. Future investigators looking back at our time might see us primarily as a geological force rather than a cultural phenomenon. They might recognize that something intelligent was altering planetary chemistry, but they might never understand what we were thinking, what we valued, what we were trying to accomplish. We might be reduced to a thin layer of strange chemistry in the sedimentary record, notable mainly for how quickly we changed the composition of the atmosphere. This perspective forces us to reconsider what we're actually looking for when we search for traces of ancient intelligence. We're probably not going to find their equivalent of Shakespeare or Einstein. We're not going to discover their philosophical treatises or their artistic masterpieces. What we might find, if we're very lucky and very clever, are their equivalents of our landfills and our smokestack emissions. The thought is both humbling and oddly comforting. Humbling because it suggests that even the most sophisticated civilizations might be remembered primarily for their mistakes and their waste products. Comforting because it implies that intelligence leaves traces even when it doesn't intend to, even when those traces are the very things it would prefer to hide. But this raises another layer of complexity in our investigation. If ancient civilizations are most likely to be detected through their unintended consequences, then we need to understand what kinds of unintended consequences different types of civilizations might produce. And that depends entirely on what kinds of technologies they developed and how they chose to use them. Our own civilization's signature is dominated by fossil fuel combustion and industrial chemistry. We extract carbon that's been buried for millions of years and release it into the atmosphere. We create synthetic molecules that have never existed in nature. We concentrate rare elements in ways that would never occur through natural processes. These activities leave very distinctive chemical fingerprints. But what if an ancient civilization had developed along completely different technological lines? What if they had never discovered fossil fuels or had learned to use them in ways that didn't drastically alter atmospheric chemistry? What if they had developed biotechnology instead of mechanical technology, learning to modify living systems rather than building machines? Such a civilization might leave traces that we would interpret as purely biological, genetic modifications in ancient organisms that seem too sophisticated to have occurred naturally, ecosystem structures that appear designed rather than evolved, chemical signatures that suggest large-scale cultivation or biological processing rather than industrial manufacturing. The Amazon basin provides a compelling example of how subtle these traces might be. For centuries, scientists assumed that the rainforest was a pristine wilderness, untouched by human influence. But recent research has revealed that much of the forest was actively managed by indigenous peoples for thousands of years. They created complex agricultural systems, modified soil chemistry, and even influenced the genetic diversity of certain plant species. The evidence for this management is everywhere once you know how to look for it. Certain trees grow in patterns that suggest deliberate cultivation. Soils contain unusual concentrations of charcoal and nutrients that indicate intentional enrichment. Even the distribution of useful plants follows patterns that reflect human selection rather than natural dispersal. But for hundreds of years, this evidence was invisible to European scientists because it didn't match their expectations of what human technology should look like. They were looking for cities and farms and roads, not for subtle alterations to forest ecology. It took a fundamental shift in thinking to recognize the sophisticated landscape engineering hidden in what appeared to be wilderness. If similar ecological management had been practiced on a global scale millions of years ago, and if the more obvious artifacts had long since decomposed, would we have any hope of detecting it today? The chemical signatures might still be there in ancient soils and sediments, but we might interpret them as natural variations in geological processes. This possibility becomes even more intriguing when we consider the time scales involved. Our own industrial civilization has existed for only a few centuries, but it's already producing globally detectable changes in planetary chemistry. A biotechnological civilization might persist for much longer periods while leaving much subtler traces. They might achieve a kind of sustainability that we're only beginning to understand, working with natural cycles rather than disrupting them. The challenge for investigators like ourselves is learning to recognize patterns that might indicate deliberate intervention even when we don't understand the mechanisms involved. We need to look for anomalies that are too regular, too widespread, or too precisely organized to be entirely natural, even if they appear to be the result of biological rather than mechanical processes. This search requires us to think like forensic scientists examining a crime scene where most of the evidence has been systematically obscured. We're looking for subtle disturbances in what should be natural patterns, chemical concentrations that don't match expected distributions, isotope ratios that suggest processing or refinement, biological patterns that seem too organized to be coincidental. But we also have to be extraordinarily careful not to see intelligence where none exists. Nature itself is remarkably creative and can produce patterns that appear designed even when they're entirely natural. Crystalline structures form with geometric precision. Biological systems organize themselves into complex, apparently purposeful arrangements. Even purely physical processes can create patterns that seem too regular to be accidental. The key is learning to distinguish between patterns that could arise through known natural processes and patterns that require something else, something that might have been deliberate. This distinction becomes increasingly difficult the further back in time we look, because our understanding of ancient natural processes is necessarily incomplete. Consider the banded iron formations that appear in rocks from the early Earth. These structures show incredibly regular layering patterns that suggest cyclical processes operating over millions of years. The conventional explanation involves complex interactions between ocean chemistry, atmospheric composition, and early microbial life. But the regularity of these patterns is striking, almost engineered in appearance. Most scientists assume these formations represent natural processes that we don't yet fully understand. And they're probably right. But the assumption itself is worth examining. How do we decide what counts as a natural process, and what might indicate intervention? How regular can a pattern be before we start to suspect that something was organizing it deliberately? These questions don't have easy answers. And that's exactly what makes this investigation so challenging and so valuable. It forces us to think more carefully about the nature of evidence, about the limits of our current understanding, and about the assumptions we bring to our interpretation of the natural world. There's also the haunting possibility that we might be looking at evidence of ancient intelligence right now without recognizing it. The geological record is full of anomalies and patterns that don't have entirely satisfactory natural explanations. Most of these are probably the result of processes we don't yet understand. But some might represent something else entirely. The distribution of certain rare elements in ancient rocks sometimes shows patterns that are difficult to explain through known geological processes. Isotope ratios occasionally appear in combinations that don't match our models of how natural systems behave. Even the timing of certain geological events sometimes seems too coincidental, too precisely coordinated to be entirely accidental. These anomalies sit quietly in the scientific literature, neither fully explained nor actively investigated. They're classified as interesting curiosities, geological puzzles that might be solved someday when we understand natural processes better. But what if some of them represent traces of ancient technologies that we don't have the conceptual framework to recognize? This possibility requires us to maintain a delicate balance between open-mindedness and skepticism. We need to be willing to consider explanations that might seem unlikely while maintaining rigorous standards for evidence. We need to expand our imagination about what intelligence might look like, while avoiding the trap of seeing design in every unusual pattern. The ocean presents particularly intriguing possibilities for this kind of investigation. Marine sediments preserve some of the most detailed records of ancient environmental conditions, but they also represent some of the most dynamic and complex environments on the planet. Chemical signatures can be altered by biological activity, ocean currents, and geological processes in ways that are difficult to predict or account for. If an ancient civilization had been primarily oceanic, or if they had used the oceans for waste disposal or resource extraction, their traces might be scattered throughout marine sediments in ways that would be extremely difficult to detect. Ocean chemistry is influenced by so many different factors that distinguishing artificial alterations from natural variations would require incredibly sophisticated analysis. Yet the ocean also offers unique opportunities for preservation. Deep ocean basins can accumulate sediments continuously for millions of years with relatively little disturbance. These sediments contain detailed records of atmospheric composition, biological productivity, and even the chemical signatures of distant volcanic eruptions and asteroid impacts. If an ancient civilization had altered global chemistry on a scale comparable to our own industrial activities, traces of those changes might still be detectable in deep ocean sediment cores. But finding and interpreting these traces would require us to know exactly what to look for. And that's where the investigation becomes circular. We can only recognize technological signatures that resemble the ones we ourselves are creating. An ancient civilization that developed along completely different lines might have left traces that we wouldn't even think to investigate. Their waste products might look like natural minerals. Their energy sources might have operated by principles we haven't discovered. Their very concept of technology might have been so different from ours that we wouldn't recognize their achievements as artificial. This limitation forces us to be both more systematic and more imaginative in our approach. We need to catalog all the ways that intelligence might alter natural systems, not just the ways that human intelligence has altered them. We need to look for any evidence of deliberate organization or intervention, even if we can't immediately understand what kind of intervention it might represent. The search also reveals something profound about the nature of memory itself. We tend to think of memory as something that preserves the past accurately, but geological memory is selective and often misleading. It preserves some information while destroying other information. It amplifies certain signals while burying others in noise. What gets remembered depends not on what was important to the original actors, but on what happened to survive the long process of geological recycling. The most sophisticated technologies might leave no trace at all, if they were designed to work in harmony with natural systems. The most profound thoughts and achievements might vanish without a whisper. What persists might be the accidents, the failures, the unintended consequences that nobody wanted to preserve. This selective preservation creates a profound challenge for anyone trying to understand the deep past. We're not just dealing with incomplete information. We're dealing with systematically biased information that might give us a completely distorted picture of what actually happened. Our own civilization provides a perfect example of this bias. Future investigators studying our time will likely focus on our industrial activities, our fossil fuel consumption, our production of synthetic materials. They might never understand our art, our philosophy, our complex social structures. They might see us as a purely geological phenomenon, notable mainly for how quickly we altered planetary chemistry. If they're very sophisticated, they might recognize that these chemical changes required intelligence to coordinate and implement. But they might never understand what that intelligence was thinking, what it valued, what it was trying to accomplish. We might be reduced to a puzzle in their equivalent of scientific journals. An anomalous spike in atmospheric carbon that happened too quickly to be explained by known natural processes. The thought is both sobering and oddly liberating. Sobering because it suggests that even our most cherished achievements might be forgotten completely. Liberating because it implies that the search for ancient intelligence might be more hopeful than we realize. If we're leaving traces despite ourselves, then others might have done the same. Somewhere in the vast archive of geological time, there might be similar puzzles waiting to be discovered, chemical signatures that don't quite fit our models of natural processes, isotope ratios that seem too precisely organized to be coincidental, elemental distributions that suggest processing or concentration by unknown mechanisms. These traces might never tell us what ancient intelligences were thinking or what they were trying to accomplish, but they might tell us that we're not alone in time, that consciousness and complexity have emerged before and might emerge again. They might remind us that intelligence is not a cosmic accident, but a natural consequence of sufficient complexity and time. The investigation continues, carrying us deeper into questions that have no easy answers. We're searching for whispers in a record that speaks primarily in silence, looking for patterns in data that might represent nothing more than the creative chaos of natural processes. But the search itself changes us, makes us more humble about our assumptions, more careful with our conclusions, more willing to live with uncertainty. In the space between one thought and the next, in the silence between heartbeats, there might be echoes of minds that wondered about these same mysteries millions of years before we existed. Or there might be only the patient processes of chemistry and time writing their own stories in languages we're still learning to read. Either way, the mystery endures, vast and beautiful and full of possibilities we haven't yet learned to imagine. The night deepens around us, and the questions multiply like stars appearing in a darkening sky. Each answer we find opens up new mysteries, new reasons to keep searching, new ways of seeing our place in the long, strange story of consciousness on Earth. The strangest thing about searching for lost civilizations isn't what we might find. It's what we've already found and dismissed. Right now, sitting in laboratories and museums around the world, there are samples and specimens that contain patterns too regular to be entirely natural, too organized to be coincidental, too precisely arranged to be accidents of geology. Most of these anomalies have been filed away as curiosities, interesting but unexplained variations in the natural world. But what if some of them aren't variations at all? What if they're messages written in a language we don't recognize by minds that thought in ways we can barely imagine? Consider the peculiar case of what geologists call concretions. These are roughly spherical formations found in sedimentary rocks, created when minerals precipitate around some central nucleus over long periods of time. Most concretions are clearly natural, formed by well-understood chemical processes. But occasionally, researchers find examples that are almost perfectly spherical, with internal structures that seem too organized, too geometric to be entirely accidental. In the early 20th century, miners in South Africa discovered hundreds of these objects embedded in rock formations over 2 billion years old. Some showed parallel grooves around their circumference. Others had internal cavities with precise angular geometry. For decades, a few researchers wondered whether these might represent something artificial, some kind of manufactured object from an unimaginably ancient past. The scientific consensus quite reasonably attribute these formations to natural processes we don't yet fully understand. High pressure, unusual mineral compositions, perhaps biological activity we haven't recognized. The burden of proof for artificial origin is enormous, and extraordinary claims require extraordinary evidence. Most of these objects can probably be explained through conventional geology given enough time and research, but the episode illustrates something important about how we approach anomalies in the deep past. Our default assumption is always natural origin, and that assumption has served science well. It prevents us from seeing miracles where none exist, from attributing every unusual pattern to mysterious causes. But it also means that genuinely artificial objects, if they existed, would have to be absolutely unmistakable to be recognized as such. The challenge becomes even more complex when we consider that ancient technologies might not look anything like modern ones. We imagine finding metal artifacts, electronic components, clearly manufactured objects that would be obviously artificial to any observer, but what if ancient intelligence had developed along completely different lines? What if they had learned to work with living systems rather than dead materials? What if their greatest technologies were biological rather than mechanical? What if they had achieved sophistication through organic chemistry rather than metallurgy and electronics? Such technologies might leave traces that we would classify as purely natural. Genetic modifications that seem too complex to have evolved randomly, organism distributions that follow patterns too regular to be coincidental, chemical processes in ancient soils that suggest cultivation or management rather than wild growth. We're beginning to see hints of this possibility in our own world. Synthetic biology is learning to create living systems that can manufacture materials process information, even serve as construction components. It's not difficult to imagine these approaches being taken much further, creating entire ecosystems designed to serve technological purposes. A civilization based on such biotechnology might persist for millions of years while leaving traces that would be virtually impossible to distinguish from natural biological processes. Their cities might be forests, their factories might be coral reefs, their computers might be modified organisms that process information through biochemical pathways we don't understand. The Amazon rainforest provides a tantalizing glimpse of how subtle these traces might be. What European explorers saw as pristine wilderness was actually a carefully engineered landscape, shaped by indigenous peoples over thousands of years through techniques so sophisticated that we're only now beginning to understand them. The soil itself tells the story. In many areas, the earth is unusually dark and fertile, enriched with charcoal and organic matter in ways that don't occur naturally. Certain tree species grow in distributions that suggest deliberate cultivation. Even the genetic diversity of some plants appears to have been shaped by human selection over many generations. For centuries, scientists missed these signs completely because they didn't match expectations of what human technology should look like. The engineering was so elegant, so well integrated with natural systems, that it appeared to be wilderness even to trained observers. It took decades of careful research and a fundamental shift in thinking to recognize the sophisticated management hidden in what seemed to be untouched forest. If similar landscape engineering had been practiced on a global scale millions of years ago, and if the more obvious artifacts had long since decomposed, would we have any hope of recognizing what remained? The chemical signatures might still be there in ancient soils and sediments, but we might interpret them as natural variations in geological processes. This possibility forces us to expand our definition of what we're looking for. We're not just searching for familiar technologies implemented by unfamiliar beings. We're potentially searching for unfamiliar technologies that might not look like technology at all, at least not to minds trained to recognize mechanical and electronic systems. The ocean presents particularly intriguing possibilities in this regard. Marine environments offer unique opportunities for biotechnology. Living systems that can process minerals from seawater, organisms that can create structural materials from dissolved calcium and silicon, biological networks that could span ocean basins while remaining virtually invisible to surface observation. If intelligence had evolved in these vast underwater realms, it might have developed technologies based entirely on marine biology. Their equivalent of cities might be vast coral-like structures that would appear natural to casual observation. Their transportation networks might be modified organisms that could carry information or materials across oceanic distances. Their manufacturing processes might use biological chemistry to create materials with properties we achieve through industrial methods. Such a civilization might leave traces in the chemistry of ancient ocean sediments, subtle alterations in mineral distributions that suggest processing or concentration by biological systems. But distinguishing these signatures from natural processes would require incredibly sophisticated analysis and a willingness to consider possibilities that stretch our current understanding of what life can accomplish. There's also the unsettling possibility that some of the patterns we see in the natural world today might not be entirely natural. Evolution is a powerful creative force, capable of producing structures and behaviors of extraordinary complexity and apparent design. But evolution also operates through random mutations and environmental pressures, creating patterns that reflect the constraints and opportunities of particular ecological niches. What if some of the patterns we attribute to evolution actually reflect artificial selection by long-vanished intelligences? What if certain species carry genetic modifications that were introduced millions of years ago by civilizations that learned to engineer life itself? What if some of the ecosystems we consider natural are actually the remnants of vast biological technologies that have been operating autonomously for geological ages? These questions push at the boundaries of what we can reasonably investigate with current methods. Distinguishing between natural evolution and ancient genetic engineering would require us to understand evolutionary processes in far greater detail than we currently possess. We would need to identify genetic patterns that are too complex, too precisely organized, or too functionally sophisticated to have arisen through random mutation and natural selection. But the possibility remains tantalizing. Life on Earth shows evidence of remarkable coordination and cooperation at scales that seem to transcend individual organisms. Forest ecosystems share resources through underground fungal networks. Ocean plankton coordinate their behavior across vast distances. Even microbial communities show levels of organization that suggest communication and planning. Most of these phenomena can probably be explained through conventional evolutionary biology. Complex systems naturally develop emergent properties that can appear designed even when they arise through purely random processes. But some patterns might represent something else. The lingering traces of deliberate intervention by intelligences that understood biological systems far better than we currently do. The search for these traces requires us to think like detectives examining evidence that has been systematically obscured. We're looking for patterns that are too regular, too widespread, or too precisely coordinated to be entirely coincidental. Chemical signatures that suggest processing or refinement. Biological structures that seem too sophisticated for their apparent function. Ecosystem behaviors that appear to serve purposes beyond the immediate survival needs of individual organisms. But we also have to be extraordinarily careful not to see intelligence where none exists. The history of science is filled with examples of phenomena that seemed mysterious or designed until we understood the natural processes behind them. Crystal formation creates geometric patterns of stunning regularity. River systems carve landscapes that appear deliberately planned. Even purely physical processes can produce structures that seem too organized to be accidental. The key is learning to distinguish between patterns that can arise through known natural processes and patterns that might require something else, something that might have been deliberate. This distinction becomes increasingly difficult the further back in time we look, because our understanding of ancient natural processes is necessarily incomplete. Consider the remarkable precision of certain geological formations. Some sedimentary layers show rhythmic patterns that suggest cyclical processes operating over millions of years with clockwork regularity. Some mineral deposits show concentrations and purities that seem almost too perfect to be natural. Some rock formations display geometric properties that appear deliberately engineered. Most geologists assume these features represent natural processes operating under conditions we don't yet fully understand. And they're probably right. But the assumption itself reveals something important about how we approach anomalies in the geological record. We have a strong bias toward natural explanations. And that bias shapes what we're willing to consider as evidence. This conservative approach has served science well, helping us avoid the trap of attributing every unusual phenomenon to mysterious or supernatural causes. But it might also make us systematically blind to genuine traces of ancient intelligence, especially if those traces don't match our preconceptions about what technology should look like. The investigation requires us to maintain a delicate balance between skepticism and openness. We need to be willing to consider possibilities that might seem unlikely while maintaining rigorous standards for evidence. We need to expand our imagination about what intelligence might accomplish while avoiding the temptation to see design in every unusual pattern. There's something both humbling and exhilarating about this uncertainty. Humbling because it reminds us how much we don't know about our own planet's history. Exhilarating because it suggests that reality might be far stranger and more wonderful than our current theories predict. The geological record stretches back over 4 billion years, representing a vast library of information about conditions and processes that operated long before complex life appeared on Earth's surface. Most of that library remains unread, not because we lack the tools to examine it, but because we're only beginning to understand the languages in which it's written. If intelligence had arisen multiple times during that vast span, its signatures might be scattered throughout the record, waiting for investigators sophisticated enough to recognize them, or they might have been erased entirely by the relentless recycling of geological processes, or they might be hiding in plain sight, misclassified as natural phenomena, because we lack the conceptual framework to see them as anything else. The beauty of this mystery lies partly in its persistence. Unlike many scientific questions that can be definitively answered through careful experiment and observation, this one might remain forever open, forever challenging us to think more carefully about evidence and assumptions. It prevents us from becoming too comfortable with our current understanding, too confident in our theories about how the world works. Every unusual rock formation becomes a potential clue. Every anomalous chemical signature becomes worth investigating. Every pattern that seems too regular to be entirely natural becomes a question mark in the vast equation of planetary history. The search changes how we see the world around us, making us more attentive observers, more careful interpreters, more humble about the limits of current knowledge. In the silence between geological layers, in the space between one sedimentary formation and the next, there might be stories waiting to be told. Stories of minds that wondered and built and dreamed in ways we can barely imagine. Or there might be only the patient processes of chemistry and physics, creating their own complex narratives through mechanisms we're still learning to understand. Either way, the investigation continues, carrying us deeper into questions that challenge our most basic assumptions about intelligence, technology, and our place in the long history of our planet. The night deepens around us, and the mystery expands like darkness, filling a vast cavern, revealing new chambers and passages with every step we take into the unknown. The most unsettling realization in this entire investigation might be how little we actually understand about the planet we call home. We think of Earth as familiar territory, mapped and measured and cataloged, but the truth is that we've barely scratched the surface of its deeper mysteries. The ocean floors remain largely unexplored. The deep continental crust is accessible only through indirect measurements, and the vast majority of geological time remains as mysterious to us as the far side of the moon. This ignorance creates a peculiar kind of blindness. We can only see what we know how to look for, and we can only interpret what fits within our existing frameworks of understanding. An ancient civilization that operated by principles we haven't discovered, using technologies we can't imagine, might have left traces that we encounter regularly without ever recognizing them as artificial. Consider the strange case of certain mineral formations that appear in very old rock layers. Some show crystalline structures that are remarkably pure and geometrically precise, formed under conditions that are difficult to reproduce in laboratory settings. Others display internal patterns that seem almost too organized, too purposeful to be entirely natural. Most geologists assume these represent natural processes operating under extreme conditions we don't yet understand. But what if some of them represent something else? What if ancient intelligences had learned to grow materials rather than mine them, to cultivate crystals the way we cultivate crops? What if they had developed manufacturing processes based on biological or chemical principles that we haven't discovered? Such technologies might leave behind products that would appear natural to our eyes, especially after millions of years of geological processing. A manufactured crystal might be indistinguishable from a natural one if the manufacturing process worked by accelerating or directing the same chemical reactions that occur in nature. A biotechnological product might look like a particularly complex biological structure, interesting but not obviously artificial. The challenge becomes even more complex when we consider the possibility of what we might call invisible technologies, systems that operate without leaving obvious physical traces, that work by manipulating energy or information rather than matter. If an ancient civilization had learned to harness electromagnetic fields, to process information using quantum effects, or to manipulate matter at the molecular level, their technologies might be virtually undetectable. Using conventional archaeological methods, we're beginning to see hints of such possibilities in our own technological development. Quantum computers process information using principles that leave no obvious physical traces. Nanotechnology manipulates matter at scales too small to be easily observed. Even our digital technologies are becoming increasingly miniaturized and ephemeral, storing vast amounts of information in ways that would be virtually invisible to investigators who didn't know exactly what to look for. An ancient civilization that had taken such approaches much further might have achieved extraordinary sophistication while leaving almost no detectable traces in the geological record. Their cities might have been constructed from materials that decompose completely over geological time. Their manufacturing processes might have operated at molecular scales, leaving behind only subtle alterations in the chemical composition of surrounding materials. Even their waste products might be undetectable if they had learned to recycle materials completely or to design technologies that produced no unwanted byproducts. A truly advanced civilization might have achieved what we now call sustainability, creating closed-loop systems that left no trace of their existence once they were no longer maintained. This possibility is both inspiring and deeply troubling. Inspiring because it suggests that technological sophistication need not inevitably lead to environmental destruction. Troubling because it implies that we might never find evidence of such civilizations, no matter how carefully we search. The ocean presents particularly intriguing possibilities for invisible technologies. Water conducts electricity, supports complex chemical reactions, and provides a three-dimensional medium for information storage and processing. An aquatic civilization might have developed technologies that operated entirely through the manipulation of dissolved minerals, electrical currents, or chemical gradients in seawater. Such technologies might leave no physical artifacts at all, operating instead through subtle alterations in ocean chemistry that would be virtually impossible to distinguish from natural variations. Even large-scale construction projects might be undetectable if they used biological processes to grow structures from dissolved materials, creating formations that would appear to be natural coral reefs or mineral deposits. The deep ocean offers another layer of concealment. At depths where sunlight never penetrates, where pressure reaches crushing extremes, entirely different forms of life have evolved using chemical energy sources that don't exist near the surface. If intelligence had emerged in these alien environments, it might have developed along lines so different from our own that we wouldn't recognize it as intelligence at all. Consider the remarkable organisms that cluster around deep-sea hydrothermal vents. These creatures survive in conditions that would instantly kill most surface life, using chemical processes that seem almost magical to land-dwelling observers. They build complex structures from dissolved minerals, create living networks that span vast distances, and coordinate their behavior in ways that suggest communication and planning. Most of these phenomena can be explained through conventional biology, but some patterns seem almost too sophisticated, too precisely organized to be entirely natural. If intelligence had evolved in these environments and had learned to work with the same chemical processes, it might have achieved remarkable things while remaining completely invisible to surface observation. The possibility becomes even more intriguing when we consider that the deep ocean preserves some of the most detailed records of ancient environmental conditions. Sediments accumulate slowly but continuously in abyssal basins, creating archives that span millions of years with remarkable fidelity. If ancient intelligences had left chemical signatures in these environments, they might still be detectable today, but finding and interpreting such signatures would require us to know exactly what to look for, and that knowledge might be impossible to acquire without first understanding the technologies that created them. We're caught in a circular problem where we need to know what we're searching for in order to find it. But we can't know what to search for until we've found it. This circularity extends to almost every aspect of the investigation. We interpret unusual patterns as natural because we don't have frameworks for recognizing them as artificial. We dismiss anomalies as measurement errors or unknown natural processes because artificial explanations seem too unlikely. We miss evidence because it doesn't match our expectations of what evidence should look like. The problem is compounded by the sheer scale of the search. Earth's geological record spans over 4 billion years and covers an entire planet's worth of environments and processes. Even if ancient technological signatures exist, they might be scattered so thinly through space and time that we would need extraordinary luck to encounter them. Consider how difficult it would be for future investigators to find evidence of our own civilization if they didn't know when and where to look. Our technological signature is currently concentrated in just a few centuries, and primarily on land surfaces that represent less than 30% of the planet. If future searchers happen to examine ocean sediments from the wrong time period, or terrestrial formations from before the industrial age, they might conclude that no technological civilization had ever existed on Earth. The challenge becomes even more daunting when we consider that any ancient civilization would have existed in a very different world than our own. Continental positions were different. Ocean configurations were different. Even the composition of the atmosphere and the length of the day were different. The environmental contexts that might have supported ancient intelligence might be so alien to our experience that we can't imagine what forms that intelligence might have taken. This alienness extends beyond just environmental conditions. The evolutionary pressures that shaped ancient life were different from those operating today. Different atmospheric compositions might have favored different types of metabolism. Different ocean chemistry might have supported different forms of marine life. Even different gravitational conditions, as the planet's rotation slowed over geological time, might have influenced how life developed and organized itself. If intelligence had emerged under such different conditions, it might have evolved along lines that are literally unimaginable to us. Not just different technologies, but different ways of thinking, different approaches to problem solving, different concepts of what constitutes intelligence or civilization. We tend to assume that intelligence naturally leads to certain outcomes: tool use, language, social organization, technological development. But these assumptions are based on observing exactly one example: our own species' particular evolutionary path. Intelligence might be far more diverse and strange than we realize. An aquatic intelligence might never develop fire or metallurgy, but might achieve extraordinary sophistication in biochemistry and organic materials. A collective intelligence might never develop individual tools, but might coordinate group behavior in ways that accomplish engineering projects on continental scales. A microscopic intelligence might operate at temporal and spatial scales so different from our own that we would never recognize its activities as deliberate. These possibilities force us to question not just what we're looking for, but what we mean by intelligence itself. Are we searching for minds that think like ours? Or are we open to forms of awareness and purposefulness that might be completely alien to our experience? The question becomes particularly acute when we consider the possibility of intelligence that operates on geological timescales. What if some forms of awareness think in terms of millions of years rather than seconds or minutes? What if they plan and execute projects that span entire geological epochs, working so slowly and patiently that their activities would be invisible to creatures like ourselves who live for only decades? Such intelligence might be operating around us right now, shaping planetary processes in ways that we interpret as purely natural, because we can't perceive the time scales on which they operate. Continental drift might be partially guided. Ocean currents might be subtly managed. Even climate patterns might reflect interventions by minds that think in terms of geological time. The possibility sounds like science fiction, but it's not scientifically unreasonable. Intelligence is an emergent property of complex systems, and complex systems can organize themselves at any scale given sufficient time and energy. If awareness can emerge from the interactions of neurons in a brain, why couldn't it emerge from the interactions of ecosystems across a planet? We're beginning to see hints of such large-scale organization in Earth's natural systems. The Gaia hypothesis suggests that the entire planet might function as a kind of self-regulating organism, maintaining conditions suitable for life through feedback mechanisms that operate across geological time. Whether this regulation reflects intelligence or simply emergent properties of complex systems remains an open question. But the distinction between intelligence and complex emergent behavior might be less clear than we assume. If a system exhibits purposeful behavior, responds adaptively to changing conditions, and maintains stability through sophisticated feedback mechanisms, at what point does it become reasonable to call that system intelligent? These questions push us toward the deepest mysteries of consciousness itself. We don't really understand what intelligence is, how it emerges from physical processes, or what forms it might take under different conditions. Our search for ancient civilizations is ultimately a search for other minds, other forms of awareness that might have looked out at the universe and wondered about the same questions that puzzle us. Whether we find evidence of such minds or not, the search itself changes how we think about intelligence, consciousness, and our place in the vast story of our planet. It makes us more humble about our assumptions, more careful with our interpretations, more willing to consider possibilities that stretch our imagination. In the silence between one geological layer and the next, in the space between one thought and another, there might be traces of awareness that operated by principles we haven't discovered, using technologies we can't imagine, thinking thoughts that would be utterly alien to our experience. Or there might be only the patient processes of chemistry and physics, creating their own complex patterns through mechanisms we're still learning to understand. Either way, the mystery endures, vast and beautiful and full of possibilities we haven't yet learned to imagine. The investigation continues, carrying us deeper into questions that have no easy answers, reminding us that the universe is far stranger and more wonderful than our theories suggest. In the end, perhaps that sense of wonder is the most valuable thing we can discover, regardless of what other secrets might be hidden in the deep history of our world. As we reach the end of this long journey through deep time and deeper mysteries, perhaps the most profound realization is not what we've discovered, but what we've learned to accept about the nature of uncertainty itself. We began this exploration asking whether we might be the first civilization to emerge on Earth. And while we haven't found definitive answers, we've discovered something perhaps more valuable. We've learned to be comfortable with questions that may never be fully resolved. The silence in the geological record speaks volumes, but it speaks in whispers rather than declarations. Every chemical anomaly we've examined, every unusual formation we've considered, every pattern that seems too regular to be entirely natural, all of these remain tantalizing possibilities rather than conclusive evidence. And perhaps that's exactly as it should be. Science often progresses not by answering old questions, but by teaching us to ask better ones. The search for ancient civilizations has forced us to reconsider our assumptions about intelligence, about technology, about the very nature of what leaves lasting traces in our world. It has made us more sophisticated observers of our own planet, more careful interpreters of ambiguous evidence, more humble about the limits of what we can know with certainty. We've seen how our own civilization is writing its signature into the geological record right now, through chemical changes that will be detectable millions of years from now. Carbon isotope ratios altered by fossil fuel combustion. Synthetic polymers scattered across the globe. Radioactive isotopes from nuclear testing. These traces will persist long after our cities have crumbled and our digital archives have decayed, telling future investigators that something intelligent once altered planetary chemistry on a massive scale. But we've also seen how selective and unreliable geological memory can be, how most traces of complex activity disappear completely over deep time, how even the most sophisticated civilizations might be reduced to thin chemical signatures in ancient rocks, their thoughts and dreams and achievements lost forever to the patient recycling of the Earth's surface. This understanding brings both humility and perspective. If we ourselves might be remembered primarily through our waste products and chemical byproducts, if our greatest achievements might vanish while our pollution persists, then perhaps any ancient civilizations that preceded us faced the same challenges. Perhaps they too struggled with questions about sustainability, about leaving positive legacies, about being remembered well by whatever minds might follow them. The possibility that intelligence has emerged multiple times on our planet, only to disappear, leaving barely detectable traces, suggests both the preciousness and the fragility of consciousness itself. Each mind that opens to awareness of the universe around it represents an extraordinary achievement, a temporary victory of complexity over entropy. And each time such awareness disappears, the universe loses something irreplaceable. Yet the search itself offers a kind of hope. Even if we never find conclusive evidence of ancient civilizations, the very fact that we can conceive of such possibilities, that we can imagine forms of intelligence different from our own, that we can wonder about minds that might have contemplated these same questions millions of years before us, all of this suggests something profound about the nature of consciousness itself. Intelligence appears to be not just a tool for survival, but a way the universe becomes aware of itself. Through conscious minds, matter learns to contemplate its own existence, to ask questions about meaning and purpose, to reach across vast spans of time and space in search of connection and understanding. Whether we are the first such minds to emerge on Earth or merely the latest in a long series, we participate in something larger than ourselves. The deep time we've explored tonight stretches back over 4 billion years, representing countless opportunities for complexity to emerge, for awareness to develop, for intelligence to look up at the stars and wonder about its place in the cosmic story. Most of those opportunities may have led nowhere, ending in extinction or evolutionary dead ends. But some, perhaps many, might have led to forms of consciousness we can barely imagine. If such minds existed, they face the same fundamental questions that puzzle us today. What does it mean to be aware in a universe that seems mostly unconscious? How can temporary beings create lasting meaning? What responsibilities do conscious creatures have toward the world that gave them birth? These questions may be universal, asked by every form of intelligence that achieves sufficient complexity to contemplate its own existence. The ocean floors we've barely explored, the deep crustal rocks we can only sample indirectly, the vast archives of sedimentary layers that remain unread, all of these might contain traces of such questioning minds. Chemical signatures of their technologies, subtle alterations to natural systems that reflect their presence, patterns too organized to be entirely coincidental. Or they might contain only the creative chaos of natural processes, beautiful and complex, but devoid of intentional design. Either possibility leaves us with wonder. If we are alone in time on our planet, it makes consciousness seem all the more precious and fragile. If we are not alone, it suggests that awareness and intelligence might be fundamental features of how complex systems organize themselves, emerging naturally whenever conditions permit sufficient complexity and stability. The investigation continues, will always continue, because the questions it raises are more valuable than any answers it might provide. Every unusual rock formation becomes a potential clue. Every chemical anomaly deserves investigation. Every pattern that seems too regular to be natural becomes worth examining more carefully. The search changes how we see our world, making us more attentive observers and more thoughtful interpreters of the evidence around us. But perhaps most importantly, it reminds us that mystery is not the enemy of knowledge, but its deepest source. The unknown doesn't diminish what we understand. It enriches it by providing context and perspective. The possibility that we might not be the first intelligent species to emerge on Earth doesn't make us less special. It connects us to a larger story of consciousness and complexity that spans geological time. As we conclude this journey through ancient mysteries and uncertain evidence, the night around us seems filled with possibilities. In the silence between thoughts, in the space between heartbeats, there might be echoes of minds that wondered and built and dreamed long before we existed. Or there might be only the patient processes of chemistry and time, creating their own intricate patterns through mechanisms we're still learning to understand. Either way, we are here now, conscious and curious, capable of asking these questions and following them wherever they lead. We can look backward through deep time and wonder about what came before. We can look forward and imagine what might come after. We can contemplate our place in the vast story of intelligence and awareness on our planet. The search for ancient civilizations ultimately becomes a search for understanding ourselves. What does it mean to be conscious? How do we create lasting meaning in a universe of constant change? What legacy will we leave for whatever minds might follow us? These questions don't have simple answers, but asking them changes us, makes us more thoughtful about our choices and more aware of our responsibilities. The mystery endures, vast and beautiful and full of possibilities we haven't yet learned to imagine. The geological record keeps its secrets, revealing them slowly and selectively to investigators patient enough to listen to its whispered stories. The ocean depths remain largely unexplored, hiding whatever traces of ancient activity might lie buried in their sediments. The future remains unwritten, waiting for us to decide what kind of signature we want to leave in the planet's long memory. In the end, perhaps the most profound discovery is not whether ancient civilizations existed, but that we are capable of imagining they might have. The very ability to conceive of other forms of intelligence, to wonder about minds that might have thought thoughts we cannot imagine, to search for traces of awareness across geological time, all of this speaks to something extraordinary about consciousness itself. We are the universe becoming aware of itself, matter learning to contemplate its own existence, time discovering its own depth and meaning. Whether we are the first such awakening on our planet or merely the latest, we participate in something magnificent and mysterious that connects us to every other mind that has ever wondered about its place in the cosmic story. The night deepens, and our questions multiply like stars appearing in a darkening sky. Each mystery we encounter opens up new possibilities, new reasons to keep searching, new ways of seeing our connection to the deep history of our world. In the silence in the stone, in the chemistry and the time, there are stories waiting to be told, questions waiting to be asked, wonders waiting to be discovered, and so the search continues, carrying us ever deeper into the beautiful uncertainty of what it means to be conscious in a universe full of mysteries. We may never know for certain whether we are alone in time on our planet, but the questioning itself enriches us, connects us to something larger than ourselves, reminds us that wonder is perhaps the most human response to the vast and ancient world we call home. Sleep well, fellow travelers through time. In your dreams tonight, You might find yourself walking through landscapes that existed millions of years before you were born, perhaps encountering traces of minds that asked these same questions in ages long past. Or you might simply rest in the quiet knowledge that consciousness itself is the greatest mystery of all, and that by wondering about it, we participate in the universe's ongoing attempt to understand itself. The questions remain open, the mysteries endure, and the search for understanding